So, in the last few lectures we have discussed transport into a finite domain, first in a Cartesian coordinate system and then in a cylindrical coordinate system. In the Cartesian coordinate system we had heat transfer between two plates that were maintained at constant but different temperatures. Okay. Initially the temperature within the medium between the plates was uniform, and at time t is equal to 0 the temperature of one of the plates was instantaneously increased, and we examined how the temperature increases throughout the domain. In that case we had used a method called separation of variables, that is, you express the temperature field in terms of as a function of z times a function of t for the unsteady transport. We express the temperature field in terms of two parts. One is the steady part plus the transient part. The steady part is the solution in the limit as time goes to infinity, and the transient part is the difference between the instantaneous temperature and the steady temperature. And the transient temperature had homogeneous boundary conditions, because the total temperature and the steady temperature satisfied the same boundary conditions on the two boundaries, and therefore the transient part of the temperature satisfied homogeneous boundary conditions. So, for the transient part the boundary conditions were homogeneous. The transient temperature was equal to 0 on both the boundaries. The temperature was non-zero at initial time. Okay, so, there was forcing at initial time. Okay. For this we used separation of variables, where we expressed the transient part of the temperature as the product of a time dependent and a spatially dependent part. Okay. And we reduced the diffusion equation to a left side that depended only on time and a right side that depended only upon the spatial coordinate. Each of those has to be a constant, okay, and that constant has to be negative, so that the transient part decreases to 0 as time goes to infinity, so that you reach back the steady temperature. So, in this procedure we had expressed the transient part as the sum of a series of functions, sine functions in a Cartesian coordinate system, Bessel functions in a cylindrical coordinate system. Okay. And each of these temperatures, each of these functions was orthogonal to every other function. So, we had a series of functions such that the integral of two different functions over the domain was equal to 0, whereas a function multiplied by itself was equal to 1. So, it was basically a delta function. Okay, it was like the dot product between orthogonal vectors. Okay. So, we express that initial condition, initial temperature disturbance of the transient part as a series in these functions. Each of these has its own relaxation rate, okay, that e power minus beta n square t or e power minus I square pi square t was different for each value of I or each value of n. So, therefore, we just take the magnitude of that function multiplied by its own relaxation rate and sum over all the functions, and we end up with the solution of the equations. Okay. So, that was the procedure that we had followed. I will just complete this for a spherical coordinate system in this lecture. Okay. So, in a spherical coordinate system, if it is axisymmetric, if it is spherically symmetric, you have a sphere, r is the radial coordinate, okay, distance from the origin, theta is the azimuthal angle, and phi is the meridional angle. Okay. So, the problem we will consider, okay, for a steady solution, for example, the differential equation is 1 by r square d by dr of r square partial t by partial r is equal to 0. Okay. You can integrate this and you will get t is equal to some constant by r plus some other constant. Okay. So, if I had a spherical particle, for example, with temperature T naught at the surface, if I had a spherical particle with temperature T naught at the surface with temperature T infinity far away, okay, then B is equal to T infinity, and so T is equal to T naught minus T infinity r by r plus T infinity. Okay. So, that is the equation solution for the temperature field. You can easily verify this is equal to T naught at r is equal to capital R, and it goes to T infinity far away. Okay. For the temperature within the sphere, okay, if you have a variation in temperature within the sphere, then the temperature will relax to a final equilibrium state. That is just a state of constant temperature, okay, because you cannot have this term within the sphere, okay, because that temperature goes to infinity at r is equal to 0. So, therefore, the only solution is a constant. Okay. Okay, within the sphere, the only solution is a constant. So, for the temperature field outside the sphere, we can get the radial flux as minus k partial t by partial r, okay, which is minus k T naught minus T infinity, okay, r by r square. Okay. The total heat transfer rate, okay, Q at any distance r is going to be equal to the spherical surface area 4 pi r square into QR. Okay. I should note that there is a positive sign here, because when I take the derivative of 1 over r, I get minus 1 over r square. Okay. So, this is equal to 4 pi k into T naught minus T infinity into r. Okay. So, if I define this temperature in terms of the flux, okay, instead of the flux in terms of temperature, I will get T naught minus T infinity is equal to Q by 4 pi k r. Okay. Substituting that into the original expression, I will get T is equal to, okay, substituting that into this expression, I will get T is equal to Q by 4 pi k r. Okay. So, this is the solution in terms of the total heat transfer rate. Okay. Now, here next, so this is the steady solution. Outside the sphere, the solution has to go as 1 over r. Inside the sphere, a constant is the steady solution. Okay. So, let us go to the transient part. Okay. Let us examine the transient part, unsteady conduction in a sphere. Okay. So, the problem is that I have a sphere initially at temperature T1, immersed in a medium at temperature T infinity at temperature T naught. Okay. Okay. So, initially the temperature is T1 throughout the sphere. So, if I plot the temperature as a function of radius, okay, it is a function of radius, this is capital R, okay, temperature. Initially the temperature throughout the sphere is at T1, okay, and it decreases at the surface to T naught. Okay. So, this is T is equal to T1, T equals T naught, okay, and as time progresses, because of conduction, the temperature will decrease throughout the sphere. Okay. Until in the long time limit T is equal to T naught everywhere. Okay. In the long time limit the temperature is uniform throughout the sphere. Okay. So, how do we solve this problem? Okay. So, we use a spherical coordinate system. Temperature field is given by partial T by partial T is equal to 1 by r square d by dr of r square partial T by partial r. Okay. Define the scale temperature as T star is equal to T minus T naught by T1 minus T naught. Okay. So, that this corresponds to T star is equal to 1, this corresponds to T star equal to 0. Okay. So, therefore, T star varies between 1 and 0. Okay. And r star is equal to r divided by r, where r is the radius of the sphere. Okay. And the time coordinate is defined as alpha t by r square. Okay. The time coordinate is defined as alpha t by r square. Okay. My apologies, there is a mistake here. There should be a thermal diffusivity in this, multiplying the diffusion term. Okay, there should be a thermal diffusivity in the equation multiplying the diffusion term. There are no sources or sinks in this coordinate system. Okay. So, in terms of this, the temperature field becomes partial T by partial T is equal to 1 by r star square partial by partial r star of r square partial T by partial r star. Okay. What are the boundary conditions? Boundary conditions at r star is equal to 1, that is on the surface, right. We know that T is equal to T naught, which implies that T star is equal to 0. There is no other physical boundary at r star is equal to 0, because it is just the center of the sphere. Okay. However, there is a coordinate boundary, because the radial coordinate varies between 0 and 1. Therefore, there is a coordinate boundary at r is equal to 0. Okay. And at that coordinate boundary, you require that the slope has to be 0. Okay. As I have shown in this graph, I have shown essentially that the slope is equal to 0 at this boundary. If the slope were non-zero at this boundary, say that you had some figure that looked like this, right, then there is a non-zero heat flux at the axis, okay, which should not be there, because there is no generation of heat at the center. Okay, at the center. Okay. If you approach this axis from different directions, you will get different gradients. Okay, you will get different gradients. Okay. So, the only way that you get the same gradient regardless of which direction you approach the center of the sphere in a 3-dimensional space is if partial T by partial r is equal to 0, which implies that partial T star by partial r star is equal to 0. Okay. And the initial condition is that at T star is equal to 0, just before the sphere has been immersed in the fluid, okay, the temperature is equal to 1 for r star less than 1. That is, the surface is at temperature 0, but everywhere within the sphere the scale temperature is 1, as shown in this figure by this step function. Okay, as shown in this figure by this step function. So, those are the boundary and initial conditions for this case. Okay. We use separation of variables once again. Okay. In this case, the steady solution, as I said, is just T star equal to 0. So, T star itself is the transient solution. So, this T star, I write it as f of r star g of T star. Substitute into the equation f dg by dt is equal to g by r square d by dr of r square df by dr, okay, divide throughout by f and g. Okay. So, you will get 1 over g and you get 1 over f here. And both of these, the left side is now only a function of time, the right side is only a function of r. Therefore, these both have to be constants. Okay. These constants, it can be either positive or negative. If it is positive, then g increases exponentially in time, right. So, therefore, the transient part does not decrease to 0 as it should. Therefore, this has to be minus beta square okay. Therefore, the spatial part of the equation becomes 1 by r square d by dr of r square df by dr plus beta square f is equal to 0. Alternatively, you can write this as d square f by dr square plus 2 by r, okay. Derivative of r square is 2r, 2 by r df by dr plus beta square f, this is equal to 0. Okay. Turns out that this can be solved analytically. Okay. This can be solved analytically. Okay. Alternatively, you can multiply throughout by r square and you will get r square d square f by d r square plus 2 r df by dr plus beta square r square f is equal to 0. Okay. Turns out that this has a solution, f of r star is equal to c sine of beta r by r plus d cos. Okay. This has a solution. Okay. C sine of beta r by r plus d cos of beta r by r, okay, where the constant c and d are to be determined from the homogeneous boundary conditions, okay, from the boundary conditions at the at r is equal to 0 and at r is equal to 1. Okay. So, first is at r star is equal to 0. Okay. You can see that the boundary condition is that df by dr star, this has to be equal to 0. Okay. Clearly, the cos function does not satisfy this. Okay. The cos function goes as cos of beta r star is equal to 1 minus beta r the whole square by 2 factorial plus etc. Okay. So, cos of beta r star by r star is goes as 1 over r star plus beta square r star by 2 factorial. Okay. The derivative of this 1 over r goes as 1 over r square. Okay. So, clearly it does not satisfy this boundary condition. Okay. The sine function on the other hand, okay, the sine of beta r by r, if you expand in the binomial series, okay, this is equal to beta r by r minus beta r the whole cubed by r. Okay. This is equal to beta minus beta cubed r star square. Okay, using the binomial expansions for the sine and the cos function. Okay, using the binomial expansions for the sine and the cos function. When you take the derivative of this, derivative of beta has to be 0. Beta r square 2 beta cubed r is the derivative, that is 0 at r is equal to 0. So, this function does satisfy the boundary condition at r star is equal to 0. Okay. So the first term satisfies the boundary condition, the second term does not. Therefore, I have to set the constant d equal to 0 in order to satisfy the boundary condition df by dr star is equal to 0 at r star is equal to 0 implies that d is equal to 0. The other boundary condition, now f of r star is equal to c sine of that is the other boundary condition is that f of r star is equal to 0 at r star is equal to 1. Homogeneous boundary conditions in the spatial coordinate, both at r is equal to 0 and at r is equal to 1, the function spatial function has to be 0. Okay. This implies that either c is equal to 0, in which case the solution is trivial, or beta is equal to I times pi. Okay. The same set of eigenvalues that we had for the Cartesian coordinate system, except that in that case the eigenfunctions were just sine of I pi z. In this case it is sine of I pi r divided by r. Okay. So, this will be beta I. Okay. Therefore, the solution for the spatial part is c sine of beta I r star by r star. The solution for g from this exponential function. Okay. Okay. I equate these two parts and obtain the solution for g. Okay. G is equal to minus I pi the whole square t star. Therefore, the total solution for the temperature field is equal to summation. Okay. In general, I is equal to 1 to infinity of c sine of I pi r star by r star e power minus I pi the whole square t. Okay. This satisfies the equation, okay, because this satisfies the equation because it satisfies the equation we had got from the separation of variables procedure. Okay. We had got this equation for the separation of variables procedure. So, this satisfies this equation for all values of I, and it satisfies the boundary conditions for all values of I. Okay. So, the most general solution is a summation of this over all values of I, okay, the constant Ci. How do we determine the values of the constant Ci? Using the orthogonality relations. Okay. We know that sin I pi r times sin j pi r is an orthogonal function, it is equal to delta ij. Okay. So, in this case what we do, since we have a spherical coordinate system, right, we know that sin I pi r star sin j pi r star. Okay. The eigenfunctions are sin I pi r by r and sin j pi r by r. Okay. If I integrate, if I multiply by r square dr from 0 to 1. Okay. This is the same as the orthogonality relation we had for the Cartesian coordinate system. So, this is equal to 1 by 2 delta ij. Okay. So, this is the same as we had in the Cartesian coordinate system. So, this is equal to 1 by 2 delta ij. Okay. Because you can see that this 1 over r cancels out with this r square. R square is present because we are doing an integral in a spherical coordinate system. The differential volume element of a shell of thickness delta r or dr in a spherical coordinate system is 4 pi r square dr. Okay. So, therefore, the where r square is basically the scale factor. Okay, it's a scale factor. It's actually r square sin theta d theta d phi. Okay, so there is no dependence here on theta or phi, therefore we have integrated over theta and phi to get this factor of 4 pi, and then r square dr. Okay. And so this one you can clearly see gives you, okay, this orthogonality relation. Okay. So the initial condition T star is equal to 1 at initial time. Okay, anywhere within the sphere when r star is less than 1. At the surface it is decreases discontinuously to 0, but it is 1 everywhere within the sphere. Okay. So at T star is equal to 0, this is just equal to 1. So therefore I have sigma of I is equal to 1 to infinity C I sine of I pi r star by r star. This is equal to 1. And how do we get the coefficients? We get it from these orthogonality relations. I multiply both sides by sine of j pi r star and integrate. Okay. So therefore r square dr sine I pi r sine j pi r, each one divided by r, okay, is equal to integral r square dr sine j pi r by r. And this left side we know. Left side we know what it is. It is the same as what we derived for a Cartesian coordinate system. So I get summation I is equal to 1 to infinity of C I delta I j by 2. Okay. On the right side I have to evaluate what is this function, and I have to do it by integration by parts. Okay. I have to do it by integration by parts. Okay. So the first term, so this r will cancel out. Okay. So I will first take r is equal to u and sin j pi r is equal to v, and the first term will be integral of cos sin j pi r times the derivative of r. So I get minus r star cos of j pi r star by r star between 0 and 1. I am sorry, there is no r star in the denominator, I cancel it out. Okay. Plus integral 0 to 1 dr star cos of j pi r star by j pi. Okay. And this one has to have a j pi because I have integrated sin j pi r, so I get cos of j pi r by j pi. Okay. So this becomes, at r is equal to 0, this term is 0. At r is equal to 1, this is minus cos of j pi by j pi plus sine of j pi r star by j pi the whole square between 0 and 1. And the sine function is 0 in both cases. Okay. So therefore you get cos of j pi by j pi, which is the same as minus of, sorry, yeah, minus 1 power j minus 1 by j pi. Okay. So, this is 1 if j is even and it is minus 1 if j is odd, this cost function. There is a negative sign in front of it. Okay, so, this is what you get. On the left side, Ci times delta ij by 2 is just Cj by 2 is equal to minus 1 or j minus 1 by j pi. Therefore, the temperature field is equal to sigma of 2 into minus 1 or j minus 1 by j pi sine of j pi r by r e power minus j pi the whole square t star. J is equal to 1 to infinity. Okay, so, this is the solution for the temperature field within a spherical inclusion, very similar to what we had in a Cartesian coordinate system, except that instead of sine of I pi r by I pi z, you have sine of I pi r divided by r, okay, and the orthogonality relation turns out to be the same in this case. Okay. So, this is the solution for the temperature field for a particle, a spherical inclusion immersed in a medium in which the temperature value has a different value. Okay. So, with this we will complete our discussion of transport in one dimension, unidirectional transport, unsteady transport in a finite domain. Okay. Procedure is using separation of variables, separate the solution into the spatial and time dependent parts. Each of these parts has to be a constant once you divide throughout by f times g, and that constant has to be negative, so that you have an exponentially decreasing function, and that negative value of that constant gives you solutions, spatial solutions which are discrete, okay, which are discrete functions, each with its own discrete eigenvalue. Write it as the summation of those, and the coefficient of these in this summation is determined from the orthogonality relation. So, that is the same procedure that will be followed for all of these coordinate systems. So, with this I will complete my discussion of transport into a finite medium. Next lecture I will start discussing an oscillatory flow in a pipe, where we use a different procedure. We use complex variables in order to simplify the problem from a partial differential equation to an ordinary differential equation. I will start this in the next lecture. I will see you then.